Hello everybody and welcome back. We are going to do example 2.3.1 in this video about the relative position or the relationship between two lines. And the two lines that were given are L1, x, y, z is equal to 3, 1, minus 2 plus t times 2 minus 1, 0. And L2, which is given in symmetric form, 3 minus x is equal to z minus 1 over 2, and y is equal to 2. Now, to help us in this task, I have prepared a little review of the four possibilities for two lines in three-dimensional space. Two lines may be parallel, coincident, intersecting, or skew, and we covered these in a previous video. And the test that we had for each of these, well, parallel and coincident lines both had the direction vectors d1 and d2 of the two lines parallel, whereas intersecting and skew lines had non-parallel direction vectors. So we had to look at a second criteria to distinguish between each of those cases. And to distinguish between parallel and coincident lines, we looked at the vector p1, p2. And in parallel lines, p1, p2 was not parallel to the two direction vectors, whereas in coincident lines, p1, p2 was parallel to both. Intersecting and skew lines, the difference is that intersecting lines are coplanar, skew lines are not. So again, the vector p1, p2 was useful to test for coplanarity, and that was the triple scalar product. So p1, p2 dotted with d1 cross d2 equaled 0. That meant the vector and hence the lines were coplanar. That was the case for intersecting lines, and p1, p2 dotted with d1 cross d2 was non-zero for skew lines. So that gives us a bit of a strategy to approach our example. The first thing we're going to do is look at whether we have a parallel set of direction vectors or non-parallel. And then depending on our result, we'll proceed down to the appropriate test afterwards. So let's go back into our example. Again, 2.3.1. And L1 is given in vector form, so we can see the position vector of a point P1, which is 3, 1, minus 2. We can also read the direction vector of this line directly as it's given, so 2, minus 1, 0. L2 is going to require a little bit more work since it's in symmetric form, so we remember that those equations are all equal to t. So 3 minus x is equal to t. That tells us that x is 3 minus t. Y is equal to 2, well that's just given. And we have z minus 1 over 2 is equal to t. That is going to tell us that z is 1 plus 2t. Now here is the line in parametric form, and we can read off the point more easily now. So P2 that we can see is the point 3, 2, 1, and the direction vector d2, the coefficients of t, is minus 1, 0, 2. And so the first thing that we want to do is we want to look at these direction vectors, and we want to ask, are they parallel? In other words, is d2 some multiple of d1? And if it were, then we'd have this little system of equations. We'd have d2 is minus 1 would have to be equal to 2 times k for the x component. 0 would have to be equal to minus 1k, and 2 would have to be equal to 0 times k, or 0. So without going any further, right, we can see right away that that is not true, that we have a little inconsistent system, and therefore those two vectors are not parallel, which tells us that we are not dealing with parallel or coincident lines. Our lines our lines must be either skew or intersecting. Skew or intersecting. And so the next test that we have to do is whether the lines are coplanar or not. So we are going to examine, as our next step, we are going to examine the triple scalar product. So P1, P2 dotted with D1 crossed with D2. So P1, P2, we need to calculate that quickly, and that is just, we'll do the delta method. We'll subtract the components, so P1's minus P2 here, so 3 minus 3 gives me 0, 1 minus 2 is minus 1, and minus 2 minus 1 is minus 3. There is, no, I've done that backwards, haven't I? I did P, yes, that should be all negative. Yes, sorry about that. I should have done P2 minus P1. So there you go, we get 0, 1, 3 as the vector P1, P2. And then we're going to calculate D1 crossed with D2. So let's get that written down. So 2 minus 1, 0 crossed with minus 1, 0, 2. So we'll recopy 2 minus 1, 0, 2 minus 1, minus 1, 0, 2, minus 1, 0, bar off the first. And what are we getting here? So minus 2 minus 0, that's going to give me just minus 2, 0, minus 4, and 0, minus 1. So the triple scalar product P1, P2 dotted with D1 crossed with D2 is, so P1, P2 is 0, 1, 3 dotted with minus 2, 4, minus 1, or 0, minus 4, minus 3 is equal to minus 7, and in particular that is not 0, so our vectors are non-coplanar, and that means that the lines are non-coplanar as well, and lines, when they're non-coplanar, are skew. In the next video, we'll do a little flow chart for the steps that we went through here. We'll just summarize that in a little bit more of a easy to remember way to go through the procedure of distinguishing the relationship between a given set of lines in R3.